Hi, I'm Tim Berglund with Confluent. I want to talk to you today about freight clusters. Freight clusters are a feature of Confluent Cloud optimized for clusters of very large scale and cost sensitivity. Now, the story of freight clusters is really the story of how Confluent Cloud learned to relax and embrace cloud-native architectures. To make that make sense, let's rewind to the beginning of Kafka time, which was really designed for the world of the data center, not the cloud. So this is the world where you've got actual sheet metal boxes in a cold, noisy room, and they've got some blinky lights. Put some blinky lights here. These are loud servers, and each one of these has inside it its own storage. There is direct attached storage inside these servers. This is the birth of Kafka. There's some beautiful things about this. Like number one, you're never going to have faster storage. Okay, that is a disk on the other end of a PCIe channel from the processor. It doesn't get better. The downside is that disk might fail. That power supply, motherboard, anything might fail. And so you have to do all kinds of fancy stuff with replication between brokers. All that was built into Kafka originally. Very complex problems to solve that were solved for that world. Now, as we begin to move to the cloud, we start to see something a little different. We've got cloud instances that are still, pretty analogous to these servers. And sometimes some of them might have what we call instance storage on them. That might be a disk actually in that actual computer running in the cloud, but more likely we're going to have, let's go to a new color for this. We're going to have what we call in AWS elastic block storage, or network attached disk, or maybe an array of disks, right? So now this is on a network, and those instances are talking to the storage over a network. So already in that change from direct attached to elastic block storage or network attached storage, we've had a significant increase in latency. This is going to be a lot slower to access, but it's advantageous. It makes the scaling easier. If one of these instances goes away, we don't have to move bytes from a replica around. That sort of stays here.
In practice, the way this worked, it was still a little bit unfortunate. If you wanted it to be available across zones, you'd have to do cross-zone writes.
And a lot of it was really hanging on to the ideas of original Kafka. Like Kafka is this process and it runs on a server, and now we have servers in the cloud, so let's just run that process on those servers without really taking advantage of all the resources and the architectural options that the cloud gives us. We're not quite there yet. Now, blob storage, of course, all along, all throughout this time was definitely a thing. You'd have, we'll just draw a cloud, and these are buckets, obviously, because that's how it's organized inside blob storage. So it's there as this effectively infinite sump repository of storage. You can put things there forever and get them out. You're never going to run out of it. Again, at probably higher latency than EBS, depending on various factors. So it's a higher latency thing, but it's kind of out there winking at us, thinking, gee, maybe this could simplify things. Now, with this whole some storage is fast and some storage is slow and all that kind of stuff, there's no right kind of storage, right? There's a continuum of options. You think inside, we could draw a little graph here. We could have latency here, if you can read that angled handwriting, and cost here. And, the good old story is, registers in the processor. They're very expensive. There are a few of them. There is no faster storage, right? Level 1 cache, level 2 cache. You start to have more cache memory, and it's a little cheaper as you go down there. Main memory, a hard disk, an SSD, something over a network. You got this, if these are log scales, kind of roughly straight line there of the latency cost relationship in storage. This applies to storage. It applies to a lot of things, and it makes a lot of sense. It's darn near kind of a universal law. Along that storage cost continuum, there isn't any one of them that's correct. And as a major provider of a managed Kafka service, Confluent, we've seen use cases proliferate. We've seen people doing things with Kafka that maybe nobody really expected in the early days. Some of those use cases take monitoring and observability. Okay, it seems really obvious now, right? But somebody was the first one to use Kafka to do that. Tremendous volume of data, very high throughput. Latency, it's okay if it takes a second. It's not super sensitive to latency. Maybe on the other hand, you've got some microservices with some kind of application that's got a really tight response time latency, and those microservices are exchanging not the highest volume of data, but latency matters. Some of those are going to be higher up on this continuum. Some of them are going to be lower down, and it's nice to be able to make choices that actually fit the system that you're building. This is how we get to the current iteration of Kora. Kora is what we call our Kafka engine that runs Confluent Cloud. Kora now really, truly believes it's running in the cloud. It believes S3 exists. It is an actually cloud-native architecture. And that leads to some really cool things like these freight clusters that we're talking about. Let me tell you how it works. Now, in Kora, there are 4 main architectural components. We're going to call them storage, compute, and metadata, and finally, the unsung hero, background. Oh, all the way. So storage, compute, metadata, and background. These are 4 pluggable, swappable layers that we can put in whatever implementation we need, depending on the kind of use case we're trying to satisfy. In the case of freight clusters, which is what this story is all about, storage is S3, just like we have over here. We'll draw that again. Here's our cloud of buckets. Saw it here first. This is now the canonical representation of Cloud Blob storage in a diagram. And so all of our actual topic data is going to be written to S3. So already, like we said with freight clusters, we're saying massive volume, low cost, and we're saying latency insensitive. You can afford to give on some latency, so all that data is going to go there. That is storage. Now, how does compute work? Well, there are things that are akin to brokers in Kora, and these are now these stateless compute instances. They do not have data stored locally on them. They do not need to know necessarily anything about what's going on with the particular request, but what they're doing is they are, if you will, brokering requests from the outside. Here's me writing some code, just say, Java producer and consumer, and I can just get load balanced to whoever I want, whatever broker I want, doesn't matter. Here's this elastic pool of these stateless, I'll keep saying brokers that make that mapping happen. And each one of those is going to take that request. And now what does it need to know? It needs to know, all right, what bucket do I put this in? What bucket do I look in to read? To get messages in and out. And it's mapping those user requests onto the storage layer. And obviously you're going to see there can be other things like batching and just sort of managing the plumbing that this guy has to do. To do that, of course, it's going to have to know some metadata. So let's get started with that. Let's put this down here. This is our new metadata engine called Conflux. This is where the state of the cluster lives. And anytime there's a produce or a consume, we're going to have to know, okay, well, there's a topic associated with that. And well, there's some notion of a partition, right? That's part of the contract, part of the semantics of Kafka. Where though, here in S3, now that we think about it, it's not obvious that partitions are really a thing here. I mean, we had partitions because we had to take big topics and split them up among brokers and store them on disks. Now we've got these things that can really get as big as we need them to. You can think of it as infinite. It is for our purposes. So a partition is kind of just a metadata abstraction now. And that broker, on doing the right, still needs to know that, because I, out here, a simpleton, need to think this is just regular Kafka. And so the cloud service, much smarter than I am, will tell me what I want to know. And to do that, these brokers will actually round trip with Conflux. So the magic here, if it seems like we're kind of getting away with murder and just saying, oh, we're going to put it all in S3 and the broker's going to be stateless and it's going to be a wonderful world, it's fine. Clearly, some complexity got moved around somewhere, and that is down to here. So now this metadata server is fast enough to be in the loop of every read and write request at scale in this cluster. So that's really the innovation. And how is that done? You might be surprised or not to hear that there's a log in there. It's kind of like its own special high performance little Kafka buried inside the cloud Kafka. And there's some fairly leading edge, fairly recent computer science research that this is based on. We'll have a paper linked in the description if you want to check that out more. It's definitely worth exploring if you are into that kind of thing, because this is relatively recent developments to make all this happen. Because all the complexity that lived out there in the bad old days of Kafka on servers, some of it get pushed into the cloud provider and their blob storage implementation. They're handling replication for us. Some of it gets pushed into here. And we end up with this magical, highly scalable, incredibly low cost Kafka implementation that we can plug these things into these layers in Kora and end up with freight clusters that, for the cost of a little bit of latency, give you those other magical characteristics that you'd like. Okay, so we got storage, we got metadata. What about background here? Well, there are some other boxes. This new color here, we'll call this background. I say boxes, even that is kind of a legacy term. Instances, units of computation, servers out here that are keeping things clean. So if you think about this architecture, I'm doing some producing, and these brokers here, they don't want to keep those messages around forever. They want to kind of send them into the storage bucket. Now, maybe they don't want to send every single one, because if you look at how these things are charged for, how the billing model, it's not just what you're storing and bytes in and out, but it's also requests in and out. And you want to minimize those requests. That's a key lever to optimize the cost of a system like this. So you might want to do some batching, but you're still going to end up with some small files in these buckets. Nobody wants that. There is some optimum file size that is going to maximize performance and minimize cost. And one of the things, as an example, that this background layer is going to do is do that compaction over time. So they just help keep things clean. So you got storage, compute, metadata, background. Those are the basic layers in Kora. And this is how they're implemented to make freight clusters work. Now, of course, because they're pluggable, it's possible to plug in other implementations, because we don't just live down here. Some of us live up here. We don't want this. It's rational to pay money to get this characteristic that we need, and you'd like a cloud service that's going to accommodate you wherever you are. Kora lets you do that. That's what a truly cloud-native architecture gives you, the ability to take advantage of the infrastructure that's there or not, depending on the performance characteristics that you want to realize. And like I said before, thinking as an architect, thinking as an engineer, I love it when I can make choices. And hey, this is all good to know. Sometimes I just like to know how things work, and that's fun. But what can you actually do with it? Well, in the description below, there's a code for you to sign up on Confluent Cloud. If you haven't done that yet, you could do it. You're going to get a free trial period. You can create a freight cluster. You notice I have not given you any numbers. I'm not telling you any performance benchmarks, just kind of speaking in generalities here, because the numbers I give you don't matter. What matter is your measurements. You can go create a freight cluster. You can go set up producers, consumers, take some measurements, see how it actually works for you. Look at the pricing. Take a look and see whether this is going to unlock a use case that didn't seem economically viable to you before in Kafka, but might be now. If that's the case, I would love to hear about it, because as you know, I always love to hear about what you build. Thanks.